Hello and welcome to Lecture 3 of our Essentials of Semiconductor Device Physics course. In this lecture, we begin discussing the notion of equilibrium. Okay, so recall that our first job is to understand the meaning of this principle. And last time we discussed the meaning of the term system. We discussed what are states and that states have properties. And in the next time, we're going to discuss the notion of equilibrium. And in this lecture, we should also be able to understand the meaning of this principle. So we say that a system is in equilibrium when the properties do not change in time. So recall that these properties are state properties and that many states can have the same property. So for example, let's suppose that we look again at a gas of particles, and this time we look at the property concentration of particles. So the concentration is the property we're going to look at in this example. So suppose that we trap all the particles at the center of the container. We know that this property, this kind of concentration, is not a property of equilibrium, because if we let go of the trap, if we release the particles, then they will move randomly, and we know that after some time the concentration will be uniform. And we also know that if we do not do anything to the system, the concentration will remain uniform forever. It will not spontaneously go back to this kind of concentration, for example. So this is a property of equilibrium. We say that the system reached equilibrium because the property is not changing in time. Notice that the states are changing in time because the particles are moving. If the particles are moving, then every second the system is in a different state. But the property does not change. And we're going to see in this lecture that the meaning of this principle has to do with the fact that the reason why we have only one property now, even though the states keep changing, is that we have so many more states having this property than, for example, having this property, that it is nearly impossible that the system will spontaneously go back to having this property just because there are too few states having these properties as compared to the number of states having the property uniform concentration. Okay, so in this course, the physical system we are interested in is an electron gas. But instead of using an electron gas to describe the main ideas, I will first use an artificial example which is very analogous to the system electron gas. So this artificial example is a system of coins. So we're going to replace the electrons with coins, just to make it easier to show the main ideas of statistical physics. So the elements, the electrons now are coins, and this is an example of a binary system because the elements can only have two states, the state heads and the state tails. And we need to ascribe energy to these states. So we're going to agree that the state H has 0 units of energy and the state T has 1 unit of energy. So we say that H has U equals 0 and T has U equal 1. So for example, let's suppose we have a system of 2 coins. Then the possible states of the system are formed by all possible combinations of states of the elements of the coins. For example, HH is one state of the system. HT is another state of the system. TH is another state of the system. And they each have a different energy. So in the state HH, both coins have 0 units of energy. So the energy of this state is U equals 0. Here we have one coin having 1 unit of energy, so the the energy of this state is 1. Here we also have one coin having 1 unit of energy, so the energy of this state is also 1. And here the energy of this state is 2. Now every theory has some assumptions, and that this is also true in statistical physics. So here we have the so-called fundamental assumption of statistical physics, and this is the assumption that all states are equally probable. And we are going to assume this all the way in our course. So we don't know if this assumption is strictly speaking true, but we know that statistical physics works. So we know that this assumption is at least sufficiently good to make the theory work very well. So in our example, we have 4 states. So if we use the fundamental assumption, then we can deduce that the probability of each one of these states is 25%, 1/4 for each. But notice that the energies have different probabilities, because more than one state can have the same property. In our example, this state and this state have the same property, the same energy. So this energy is more probable than this energy and this energy. In fact, the probability of finding the system with energy 0 in our example is 25%. Of finding it with energy 1 is 50%, and finding it with energy 2 is 25%. Now let's see how this principle applies to our example. So the principle states that the state property in our example is the energy of a macroscopic system in equilibrium is always the most probable. So the most probable property in our example is energy equal 1. So according to this principle, the property of equilibrium is the most probable property. So in our example, this is the property energy equal 1. So according to this principle, in our example, the property energy equal 1 is the property of equilibrium, which means that this is the property that does not change in time. But according to the fundamental assumption of statistical physics, all states are equally probable. So if we make a measurement in this system and find it to be in this state, the fundamental assumption entails that after some time we take another measurement in the system and we can find it in this state or in this state or in this state with equal probability, since all states are equally probable. So this principle is not conveying what we should expect in our example, because in our example, if I find this system with energy U equal 1, in other words, either in this state or in this state, after some time, I have 50% of probability of finding the system with either energy 0 or energy 2, because the probability of finding the system either in this state or in this state is 50%. So I should not expect to find the system in equilibrium. In other words, I should not expect to find the system with energy U equal 1 all the time in our example. So this notion of equilibrium does not really apply to our example. We don't really have a property of equilibrium. We have a most probable property, but we cannot say that this property is the property of equilibrium, because only half of the time that we take a measurement in the system, we're going to find a system with this property. So where is the problem? Why our principle is not working in our example? And you probably have noticed that the principle is stating that the system must be macroscopic. And in our example, we have a microscopic system. We have a small system with only 2 coins. But this principle is stating that only in a big large, gigantic, macroscopic system, we should expect that the most probable energy is indeed an energy of equilibrium, is indeed an energy that does not change in time anymore. Now, to check if this principle is true in a macroscopic system, let's suppose again that we have a system of coins, and now we have n coins in our system, and we're going to plot histograms of the system, which gives in one axis the number of ways we can arrange n coins with m tails up. So each configuration, each way we can arrange these n coins is one state. So in the vertical axis of the histograms, we have the number of states, and the number of coins with tails up is the energy. So you can identify m here with the energy. So from combinatorial analysis, we can find that the number of configurations, the number of ways we can arrange n coins with m tails up is given by this equation, where this is the factorial. We're not going to discuss this equation. We're just going to use it. So here we have three examples for a different number of coins, and we have normalized histograms. So in all cases, we normalized the histogram to the peak just to make it easier to see. Okay, so let's begin by taking a look at this histogram, which assumes 100 coins. So here in this axis, we have the energy, so the number of coins with tails up, m. Here we have the normalized number of states. In other words, the number of configurations, the number of ways you can arrange 100 coins with this many tails up. So if we make an experiment, if we toss 100 coins and we try to guess the result, are we justified in expecting that it is guaranteed that we're gonna have half of the coins with tails up? In other words, that the most probable energy, which is m equal 50, will be observed? Well, from this histogram, we cannot expect that this is guaranteed. We can see that m equal 50 is indeed the most probable result. But the probability of finding 40 coins with tails up or 60 coins with tails up is still significant. So the error of the measurement or of the experiment can be interpreted as being a measure of the width of the histogram. So from this histogram, we expect that a number between 40 or 60 of coins with tails up is within an expected range. So we say that it is guaranteed that we're going to find 50 coins plus or minus 10 in this experiment with tails up. So we should not expect 80 coins with tails up, because the number of states having 80 coins with tails up is too small compared to the number of coins having between 40 and 60 tails up. The number of coins having 100 tails up, for example, is only one. So it's very, very unlikely that this will happen. 80 is still so small that we cannot even see in the histogram. 20 is so small that we cannot even see. So you should expect that the result will be 50 plus or minus 10. So here we have an error of 10 out of 50. So the width compared to the central value, to the most probable value, is significant, is 10 plus or minus 10 out of 50. So we should not expect that the result will be m equal 50. So that means that in this example, we do not have the most probable energy being an energy of equilibrium, because since all states are equally probable, and since the system keeps changing state all the time, if we find the system with a state having energy 40, after some time we can find it with having energy 30 or 60 or 50. But if we find it having an energy 50, we know that after some time it could have 60, 40, 30, so the energy will never stop changing in time. The system is not big enough. Now if you look at a system with 10,000 coins, we can see that the width compared to the center is much smaller. So that means that the fractional error, in other words, the width as compared to the central value, is much smaller for 10,000 coins than for 100 coins. And if you look at 1 million coins, we can see that the histogram is so thin that we cannot even tell its width. So the fractional error here becomes insignificant. So in this case, we can assert that the result of the experiment will be half of the coins with tails up within an error range which is insignificant as compared to the central value, as compared to 1 million divided by 2. So to give you an idea of the numbers involved, let's suppose that the system is indeed macroscopic. So when we say macroscopic, we are talking about order of moles, so 10 to the power of 23. So in this case, the width of the line is of the order of the most probable energy times 10 to the negative 12. So this is an error of only 10 to the negative 10% around the most probable energy. So this is not an error 10 to the negative 10% that we can measure, that has any physical significance. So when n is macroscopic, we're entitled to expect that the most probable energy is indeed the energy that we're going to find after some time. In other words, if we find a system with the most probable energy, the system will remain with this energy. If we toss 10 to the 23 coins, it is guaranteed that we're going to find half of them with tails up. If we toss again, it is still guaranteed that we're going to find half of them with tails up. If we toss again, it's going to be half of them with tails up, and we can toss them forever. We're going to find half of them with tails up, even though all states are equally probable. So each configuration could be accessed with the same probability in each toss experiment, but there are so many more states having half of the coins with tails up that it is guaranteed that we're going to find half of the coins with tails up in all toss experiments. Now to sum up, let's suppose that a demon draws a super list of states of the system with 10 to the 23 coins. So this is one state and it goes on and on and on. There's another state and goes on and on and on. And the list goes on and on and on. And this list has so many states and these states are so huge that only a demon could draw it. But we can imagine that we have this list. And let's suppose we collect all states having the most probable energy, so 10 to the 23 divided by 2, somewhere here. So the system can access all of the states with equal probability, and the states keep changing all the time. So even though all states are equally probable, and even though the states keep changing all the time, we know that the energy, the property of the system, will be the most probable one, just because there are so many more states having the energy 10 to the 23 divided by 2 than states having other energies, that it is guaranteed that the energy of the system will be 10 to the 23 divided by 2. And that's why we say that the most probable energy is an energy of equilibrium because this energy does not change in time, even though the states keep changing in time. So the system is in a state having the most probable energy, and after some time it goes to another state with equal probability. But due to the sheer number of states having the most probable energy, it is guaranteed that this next state will be another state having the same energy, the most probable energy. And that is why then our system, our principle is true. And as we're going to learn in a future lecture, this principle is just a funny way of formulating the second law of thermodynamics. Okay, so with that we conclude this lecture, and in the next time we're going to apply the principle we developed in this lecture to the very important problem of thermal equilibrium. So I see you next time.